So now that we're moving on to chapter 15, we're dealing with not disjoint and dependent probabilities. The best example of a dependent probability is cards. If I'm dealing a hand of cards, I'm not putting them back into the deck. And every time I deal another card, there's less cards in the deck, and there's less of the ace that you just got in the deck, so the probability changes after every deal of a card. That's dependent probabilities. Non-disjoint probabilities are the probability that you are a senior and in AP Stats. What's the probability of being a senior or being in AP Stats? Well, there are people that are in both. There are seniors that are not in AP Stats. There are seniors that are in AP Stats, so there's overlap. If I counted all the seniors and I counted all the kids in AP Stats, right, there's overlap. Some people are getting counted twice. You, seniors, would be getting counted twice, right? If I did the probability of being a senior or being in AP Stats. You would be counted as a senior. You would be counted as being in AP Stats. And then so you are getting counted twice. Okay. So the sample space is a collection of all possible outcomes. We look at conditional probabilities. This line is not supposed to be this long. Like, there's a little white out here. There. That's the way it's supposed to be. Conditional probabilities are probabilities that take into account a given outcome. The notation is probability of A with a vertical line and B. And that is read, the probability of A given B. What is the probability that you are a senior given that you're in AP Stats? What is the probability that you are 18, given that you're a senior? What's the probability that you're a junior, given that you're in AP Stats? It's all changing. It's where we're looking at a subset. Okay, back in chapter 3, we looked at the Titanic. What was the probability that you survived given you were female? Right? That was a lot higher than the probability of surviving if you were a male on that boat. And we look at it again this chapter, and we look at it based on the class of their ticket. Or the crew. Were they crew? The equation for our conditional probability is the probability of B happening, given A has already happened, is equal to the probability of A and B divided by the probability of A. We're dividing by what is given. Okay? That's how I remember. We're dividing by what's given. So the probability that both things happen divided by the probability of what was given. Then we have our general addition rule for two events. The probability of A or B is the probability of A or B. Last chapter, the probability of A and B was 0 because they were disjoint. So it's the probability of A plus the probability of B, but you have to subtract the probability of A and B because these got counted twice, right? Just like we said, if it was a senior, okay, all of the seniors in here would be counted as a senior. And then we said a senior or being in AP Stats, you would be counted as being in AP Stats. And so we would have to subtract off those of you who are seniors in the class because we counted you in both of the original probabilities, right? We counted you twice. If two events are independent, then the probability of A given B is equal to the probability of A. knowing that B happened did not change the probability that A will happen. It's the same. The probability of A given B is equal to the probability of A. This is a formula we can use to determine independence. Okay, that's a formula we can use to determine independence. We must state it in context with proper notation when we are asked about that. The last chapter, when our probabilities were independent, we could just multiply the two probabilities together. But if it's not independent, the general multiplication rule for two events, the probability A and B, is the probability of B times the probability of A given B happened, or the probability of A times the probability of B happens given A happened. And we're going to use a tree diagram to help with some of these conditional probabilities. Real quick, just in case, we have red cards. Of course, I wrote red in black. We have red cards, and we have black cards, right? The red suits are the diamond and the heart. The black suits are the club and the spade. Okay, this is a club and a spade. Obviously a heart and diamond. Okay. And each of these has an ace, a 2 through 10, a jack, a queen, and a king. Okay? So there are 13 of each denominations. Okay? These three are called what types of cards? Face cards. All right. So, like I said, it's considered common knowledge to know the deck of cards, how it's made up, how many of there are. There are 4 of every denomination, right? There's an ace that is a heart, a diamond, a spade, and a club, right? Half the deck is red, half the deck is black. Okay, and there's 52 total cards. Because 13 times 4, right? We good? One card is drawn from a standard deck of cards. What's the probability that it's an ace or a red? Okay. Or is this equation? Probability of A or B. It's a probability of, well, we're not talking about A or B anymore. Let's talk about an ace or a red. It's a probability of an ace plus a probability of red. What's the problem if I just add those together? I'm double counting how many cards? The red aces, right? So I have to subtract off the probability that a card is an ace and a red, right? Because in that probability of aces, how many are there? There's 4 aces out of 52. How many red cards are there? 26 out of 52. But the ace of hearts and the ace of diamonds is in both of those numbers, right? So we have to subtract the 2 cards that are both red and an ace. So what's my probability? 28 out of 52, which is 0.5385. Questions on that one? I pulled one card from the deck. What was the probability it was an ace or a red? 0.5385. Okay. So this is our general addition rule, and it can be applied when it's disjoint as well, because that probability of A and red would be 0, right? If I was talking about a deck of cards, well, we'll get there later. Sorry, getting ahead of myself. 2 cards are drawn without replacement. I'm not putting it back in the deck. I'm going to deal you a card, and then I'm going to deal you a second card. What's the probability that you get 2 aces in a well-shuffled deck of cards? Do you know how many times it takes to completely randomize a deck of cards? How many shuffles? 7. Yeah, where do we get that information? Chapter 11. I give that tidbit every time I play poker with people. And then everybody starts shuffling it 7 times. Okay. So what's the probability of an ace and an ace? Okay. So the first one, we don't know. Right. What's the probability that you get an ace? How many aces are there? 4. 4 over 52. Okay, well now I'm going to keep the first one out. Okay, we're going to start this deck. I have a completely fresh deck of cards. No jokers. The probability that I deal you an ace, there's 4 in the deck, right? 4 aces out of the total of 52 cards. Now, you have an ace in your hand. Given that you have an ace in your hand, what's the probability that the next card is an ace? 3 out of 51, right? There's 1 less ace in the deck, and there's 1 less card in the deck, right? So now the deck of cards has 51 to choose from, and there's only 3 aces you can get. So then that's 12 over 2652. It's just 0.00452. That's a really low probability. And I'm only dealing a card to 1 person. I'm dealing you a card, and then I'm dealing you another card. Imagine how that probability changes as I go around a table of 8 poker players. That probability every time is getting lower and lower and lower of getting 2 aces in your hand. So I need to not be so mad every time I don't get 2 aces.
So, like, can you count cards?
I cannot count cards, no.
Have you ever tried?
No.
So cool. My uncle can.
A flush. 5 hearts in a row, what's the probability of getting that? That's called a flush when you have all of the same suit. Okay? So, how many hearts are in the deck?
26.
There's 26 red. 13 of those are hearts. So the probability that my first card is a heart is what? 13 out of 52. No. It really doesn't. What's the probability that the next card is a heart? Now there's 12 hearts left, and there's 51 left in the deck. What's the probability that the next card, the third card, is a heart? 11 out of 50. What's the probability that the fourth card is? Also a heart. Now there's 10 cards left that are hearts and 49 total. And the last one, 9 out of 48. Now if you want to reduce blah, 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 I wouldn't. I would multiply across the top. 13 times 12 times 11 times 10 times 9. Anybody know how to do that with the click probability button? Just wondering if you ever got to it. There's a button, it's called NCR. Never mind, we're just not going to go there. 15,440 and 52 times 51 times 50 times 49 times 48 out of 3,118,75,200. And I get 0.0004952 because it's 4.952 times 10 to the negative 4. I got scientific notation on the calculator. So I got to move my decimal place 4 times. So, again, that's the probability of getting a flush if I'm just dealing to one person, right? Now if I'm dealing cards to 8 people, probabilities are different, right? A flush is one of the higher hands you can get. It is higher than a straight because there's more ways to get a straight. A straight is like 2, 3, 4, 5. 2, 3, 4, 5, 6. Right? A royal straight is 10, jack, queen, king, ace. And then a royal flush is when you get that's like the highest you could possibly get, right? It's the 10, jack, queen, king, ace, all in the same suit. You get that at a poker table, you're winning big. If you can keep people betting with you. That's the other part of poker, right? You gotta, if you go in too early, you lose people. I don't know. I draw one card and I look at it. Okay, I'm holding a card. It's red. What's the probability it's a heart? So what's the probability that it's a heart given it's red? Yes, 13 out of the 26. Because I know it's red, so I know I'm only choosing from the 26 red, and I know that 13 of those are hearts, 1/2. Okay. I have a card in my hand. It's a heart. Given it's a heart, what's the probability that it's red? 1, right? All of the hearts are red. There's no black hearts in poker. So if all the hearts are red, then it's 13 out of the 13. Yeah. The thinking question. Which one? Okay. Are a red card and a spade independent? Let's find out. Independent, we can say the probability of a spade. I like to practice drawing it. Given it's red, would equal the probability of getting a spade. It's the probability of A given B has to equal the probability of A if they are independent.
No, like, did you mean number 5 was part of 4?
No. The second thing I asked. Oh, I'm numbering them badly. I got it. This is 5. This is for A and for B. Better? This is for B. And this was for A. Sorry. So now we're talking about that idea of independent and mutually exclusive. Is it one or the other? Is it neither? Neither is an option. It doesn't have to be one of those two things. Okay? If it's independent, knowing that the card is red does not change the probability of getting a spade. If I know the card is red, what's the probability I got a spade? 0, right? So this probability is 0. And the probability of getting a spade is 13 over 52, or 1/4. So it's not independent. Yes. They have to equal each other to be independent. Now, is it mutually exclusive? Means mutually exclusive means the probability of a spade and red card equals 0. Is there a red spade? No. So if that probability is 0, then yes, spade and red are mutually exclusive. What's another word for mutually exclusive? Disjoint. Disjoint is the same as mutually exclusive. Number 6. What about a red card and an ace? Probability of an ace given it's red. And I can do that probability either way. A red given an ace or an ace given a red. That has to equal the probability of an ace. Are these two things independent? What's the probability of an ace if I know it's a red card? 2 out of 26, right? 1 over 13. What's the probability of an ace? 4 out of 52. Are those the same? Isn't 4 over 52 reduced to 1 over 13? Yeah. So yes, ace and red cards are independent. Are they mutually exclusive or disjoint? No. Why? Because there's 2 red aces, right? So the probability of an ace and a red is 2 over 52. If that probability is not 0, the chance of getting both is not 0. It is not mutually exclusive or disjoint. Yes?
So, like, if we were, like, saying something that's mutually exclusive, like, we technically would use, like, straight.
No.
Like, it'd be obvious.
Most of the time, yeah. I mean, sometimes the problem is going to set you up to where it gives you enough information to maybe solve for, like, if you solve this equation, it gives you the probability of A or B. And then you have to solve for this to find out if that's 0 or not. If this is 0, then it's mutually exclusive. If it's not 0, then it is not mutually exclusive. So that would be kind of a problem where it asks you to do a little bit more than just kind of like think about those probabilities. Can you have both? Right? In general, it's pretty much common sense. Can I have both? What about a face card and a king? That's my last one here. Probability of a face card and a king. Oops. That's not actually what I'm finding. I want to know if face card and a king are independent. So what's the probability it's a king given it's a face card? And then is that equal to the probability of it being a king? Probability of it being a king is 4 out of 52, which is 1 over 13. How many face cards are there? 12. There's 4 jacks, 4 queens, 4 kings. So there's 12 face cards. How many of them are kings? 4. 4/12 is 1/3. Not equaled, right? So they're not independent. Are they mutually exclusive? Is there a face card that's a king? All the kings are face cards, right? So because there are cards that are both, that's not mutually exclusive, right? The spade and the red are mutually exclusive because none of the spades are red. Your ace and face cards are mutually exclusive because the aces aren't considered face cards, right? But a king and a face card is not mutually exclusive. An ace and a red is not mutually exclusive because you can have both. Layla.
Something being like independent or not independent doesn't necessarily mean it's going to be mutually exclusive.
Correct. If it's not independent, it could still not be independent and not be mutually exclusive, right? Remember, there's that still neither of those. Suppose that the probability that a U.S. resident has traveled to Canada is 0.18, and to Mexico is 0.09, and to both countries is 0.04. What is the probability that an American chosen at random has traveled to Canada but not Mexico? Okay. So A, what's the probability that they've been to Canada but not Mexico? Well, wouldn't that be the probability that they've been to Canada minus the probability that they've been to both? Right? That 4%, right, is counted in the Canada numbers, but it's also counted in the Mexico numbers. Right? Now, clearly, this is like all of the United States, because if you were doing like Southern California, most people that live in Southern California have been to Mexico, right? But people on the other side of the country necessarily haven't been because it's not as close. Or like we're more likely to go to Vegas and Hawaii than people on the East Coast, because that's a really far flight. If you think about it, if you live in New York City and you're going to Hawaii, you have to not only fly to LA, then you have to fly to Hawaii. That's like 11 hours. So these numbers, remember, are all of the United States. Not that that matters about anything, but okay, so that's going to be what? What's the probability that a person's been to Canada? 0.18 minus the probability they've been to both, 0.04. So the probability that they've been to Canada but not Mexico is 0.14. Okay. Part B. What's the probability that they've been to Canada or Mexico? No. Or means add. Or means to add. We have to do the probability they've been to Canada plus the probability they've been to Mexico. But what's the problem with that? If I just add up those two numbers, what's the problem with that? You're double counting, right? You're double counting the people that have been to both countries, so we have to subtract off the probability they've been to Canada and Mexico, which is 0.18 plus 0.09 minus 0.04. Okay? So remember that when they are not disjoint or not mutually exclusive, we have to subtract the probability of both. And or means add. Okay, it's the and that means multiply. No, that wasn't it. Let's see, this is 0.27 minus 0.04, which is 0.23. Yes? Now, C, what's the probability they have not traveled to either? Not Canada and not Mexico. Yeah. Well, isn't the complement of not having traveled to either having been to one or the other? So the probability of neither is 1 minus the probability of Canada or Mexico. Yeah. So that's 1 minus 0.23, 0.77. Okay. So the probability of neither is 1 minus the probability of either, right? One or the other. So that was that example. Now, another way to do this problem is to look at a Venn diagram. And I want to show it to you in case you see it in the solutions. Good old Venn diagrams. Okay. We know the entire circle for the probability of Canada is 0.18, right? Yeah. We know the entire circle for Mexico is 0.09. And both is 0.04, right? So the part that does not include both, right? Not including both is your 0.14, right? And if you're not including both for Mexico, that's what? People have only been to Mexico. 0.05, right? You subtract off the both. And then you could add those together. If you put it in a bigger box, what's outside is neither. So 0.14 plus 0.4 plus 0.5 gives us that 0.23, right? And then we can find the 0.77. Sometimes that helps us find some probabilities. Now, what if it asked, what is the probability that they've been to Canada given they've been to Mexico? This problem's not in here, but we will be asked things like this. Given you know they've been to Mexico, what's the probability that they've also been to Canada? So this is where we use some of our formulas. That's the probability of Canada and Mexico, probability they've been to both, divided by the probability they've been to Mexico, divided by what's given. Clearly, these people travel, right? So what's the probability of Canada and Mexico? No. You're given the probability of Canada and Mexico. It's not 0.18 times 0.09, it's 0.04. That's the probability that they've been to both, right? So 0.04 is the probability that they've been to Canada and Mexico, divided by the probability they've been to Mexico, 0.09, which is 4/9, which is 0.444. Okay, so I'm going to write this down. What's the probability they have been to Canada given they have been to Mexico? So next one is what's the probability they have been to Mexico given they've been to Canada? So that's the probability of M given C. How does that change my calculation? That's the probability of Canada and Mexico divided by the probability of Canada. So what's given is what goes in our denominator. We divide by what's given. Because we're dividing them up. We're saying, okay, I'm only looking at the people that have been to Canada So out of that 18%, what's the probability that they've been to Mexico? So that's your 0.04 given your 0.18. Because only 4%, right, have been to both. I need a calculator for. Well, no, I don't. That's 2/9, just 0.222. Okay, and then the last question we're going to answer on this one is traveling to Canada independent of traveling to Mexico? Are they independent? So does one affect the other? It's possible. Why? You might like to travel, right? That might be something that's influencing whether you've been to either countries. You live close to one or the other places. So we have an independence formula we use. Okay, this isn't a judgment call, right? We use our formula. The formula says the probability of A given B is equal to the probability of A. So if this is true, yes, they are independent. Okay. So we're going to say the probability, we've calculated both things. We've calculated the probability of being to Canada given you've been to Mexico. We've calculated the probability of being to Mexico given you've been to Canada. So I can use either one of those, and I usually, when you get to this point in the problem at asking about independence, you've calculated the A given B. You've calculated some of those, and it doesn't matter which one you choose. Okay, I can choose either C given M or M given C. If I do C given M, that should equal the probability of what? C. Okay, the probability of being to Canada didn't change because we knew you had gone to Mexico. The probability stayed the same. That's what that means. What's the probability that they had been to Canada given they have already been to Mexico? 0.444. That's the calculation we did up here, right? And is that equal to, what's the probability they had been to Canada? 0.18. So are they independent? No. They are not independent. Now, if I had done it the other way, would I end up with the same result? Probability of M given C, is that equal to the probability of M? No. This was 0.22, and this was 0.09. Same answer. So it doesn't matter which way I choose to do that calculation, but it has to be the calculation. It's not a judgment call. Okay? Yes?
Don't you mean no, they are not independent?
No, they are not independent. You are right. You're right. No, they are not independent is what I meant to say. Okay. Other questions? In chapter 3, we looked at the Titanic and the class you were on the ship, right? First class, second class, third class, and then the crew. That's like, now it's like your balcony rooms, your outside, and then your inside. That's kind of how the cruise ships are divided up now. And then there's the people that work on the cruise ship. So now we're looking at it a little different. Did your gender affect whether or not you survived? Okay. If you've seen Titanic, the movie, you know they were like women and children first, right? But then there was, at least in the movie, there was plenty of men that found their way you know, push those children aside and get on the boat. But what was the probability? So remember, we're talking about if we look at the ship's manifest, a list of everybody that was on the Titanic, and we randomly chose a name, what was the probability they survived? What's the probability that a randomly chosen passenger survived? 711 over 2201. Right. 711 over 2201. Okay, and we're not going to bother with making these into decimals right now, but you can. What's the probability that a randomly chosen passenger or person, and not necessarily passenger, but person on the boat was male? Right, 1731 over 2201, right? We had 1,731 males, only 470 females. Why were there so few females on the boat? Why do you think there were so few females on the boat? Remember, this is not just passengers, this is all people on the boat. Emily? Right, the crew was almost all men, right? The workers, the people that were working on the boat were almost all men, right? Very few women worked back then. They just got to be along for the ride, the fateful ride. Okay, so that's why it's so disproportionate for the number of men that are on the boat and the number of females, because you're including all the workers, and all the workers were almost all men. So, what is the probability that a randomly selected passenger was a female and survived? Out of? Yeah. Yes, female and survived is the 344 out of the 2201. We're not saying given she survived. We're saying what's the probability that anybody on the boat was female and survived. Okay. Now, sometimes it is nice to look at the decimal because it's really hard to compare fractions, right? So 15% chance that a randomly chosen passenger was female and survived. What's the probability that a randomly chosen passenger was male and died? Over 2201. Yeah, put it on my keyboard. That way it doesn't get lost in my messy papers. 6197, so I'm going to round to 0.62. Okay. Now, what's the probability that a randomly selected passenger was male or died? Male or died? Well, that's male given they died. Or no, that's died given they're male.
So would you add the survived?
We're going to have to think about the, right, we're going to use our formulas. That's going to be the probability that they're male plus the probability that they died, that a person died, minus the probability that it was a male and they died. Because if we look at the males, that total, and the people that died, they're counting this twice, right? That 1364 is in both columns. If I just add those two together, it's going to be above our total. We have 1364 over 2201 plus 1490 over 2201. It can't be over 100%, right? So we're clearly counting a single group more than once. So we subtract off, oh wait, this is not right. This is our males, 1731. right? It's all the males, probability of being a male on the boat, right? So it's this, probability of dying, this, and then the both is the 1364. And so we just 1731 minus 1490 plus 1490 minus 1364 is 1857 over 2201, which is an 84.4% chance. 84.4% chance that a randomly selected passenger was either male or died. Yeah. What about female or survived? I'm running out of space. So we're going to do
470 over 2201.
so 470 over 2201 plus 711 over 2201 minus survived. Female and survived is 344 over 2201. 470 plus 711 minus 344. 837 over 2201. 38.1% or 0.381. What's the probability that they survived, given they were female? When we're looking at a contingency table like this, the probability they survived, given they're female, we can limit our denominator to the female column. So we're looking at only the females. That would be 344 out of 470, right? If we used our formula for this, which is the probability survived and female, divided by the probability of female, that probability is 344 over 2201 over 470 over 2201. So our denominators cancel, right? And that's why we can just do this calculation. So if you were a female, if you randomly chose a female on the ship, there was a 0.732%, there was a 73.2% chance that she survived. If you looked at only the females and you randomly selected a passenger, that's the likelihood she survived the trip. Yeah. Yeah, these are real numbers from the Titanic. They're not just made up, right? We have that data. So this is real. Okay. The next one is what? Probability they were male, given they survived. So looking at only the survivors. How many survivors were there? 367 male survivors out of 711 total survivors. .516. 51% of the survivors were male. What's the next one? Probability that you died, given you were a female. Well, isn't that just going to be, yeah, the 126 over the 470, which is just the complement of this, right? Survived given female or died given female. Those are the only two options. Those need to add to 1, right? If you're a female, you either died or you survived. So that's 0.268. Yep. And then what's the probability that you're male given that you died? So we took only the people that died. We randomly selected one of those passengers. What was the probability it was a male? 1364 over 1490. Yeah, 1364 over 1490. 0.915. .91% of those that died were male. And lastly, what's the probability that they were female given they survived? Right. 344 over 711. 0.484. So lastly, do you think gender and survival were independent? Do you think whether you survived that trip depended on whether you were female or male? Okay. Yes, we think it's dependent, which means no, it's not independent, right? So our formula would be A given B is the probability of A. I can pick any of these conditional probabilities I've already calculated. Any of them. Female given survived. Male given dead. Male given survived. Which one do we want to choose? Male given dead. Was that the probability of being male? Okay. Male given dead was 0.915. What was the probability that a randomly chosen passenger on the ship was male? 1731 over 2201. 0.786. Are they independent? No.
So we're right, they are very dependent.
Yes. Yes, we could say survival was dependent on a person's gender. Right? Your likelihood of surviving depended on whether you were male or female on that boat.